Hi, this is Peter with CalcBook, and today we're going to be looking at a timber beam design and specifically looking at sawn lumber. So let's take a little recap here of how we will approach this. We're going to be using the National Design Specification, also known as the NDS, and we'll be using the 2018 version. We'll be using both the specification and the design supplement, and we'll talk about those two things. So for the specification, right, that's going to give us our design procedure, our capacity equations, and then our general adjustment factors. So things like our load duration or time effect, things that are going to apply to all the different types of species that we're looking at for sawn lumber. Section 3.3 will give us our flexure equations. Section 3.4 will give us shear. 3.5 deflection, 3.6 compression, and then 3.9 will give us combined loading. And then we'll be using the supplement, right, and that gives us the all the reference design values for our various species and shapes and sizes, and it also gives us any additional specific adjustment factors for that type of member. So we'll get some additional values there as we need. So let's take a look at our problem statement. We're going to be looking at a header design, right? So we've got a floor plan there, and we've got a header that's going to be going over a sliding glass door. The length of the header is going to be 7.5 feet. We're going to be using a Douglas fir larch number 2 beam. We are going to be using a 4x size, right? This is a 2x4 wall, so we'll be using a 4x beam, and then we'll be determining what depth we need for the loading. We've got some decent loading here because we've got a porch overhang and then we've got a second story above this. So we've got some loading. We're using a dead load of 450 pounds per linear foot and then a live load of 330 pounds per linear foot. And then we're going to be using our ASD loading. So let's go ahead and open up CalcBook and we'll get started on the design. All right, I've got CalcBook open now. So we go ahead and click into our NDS 2018. Go to our timber member design. And then for this header design, we're going to need our strong axis flexure and our strong axis shear design. So we can click on confirm. All right, so we're going to go ahead and keep our loading as a beam analysis because we have our distributed load. So we'll go ahead and use the beam tool for that. We want to change our lumber type here to a visually graded dimension lumber. Our species is going to be Douglas fir larch. Our grade is going to be number 2. And our size, we said it needs to be a 4x. We don't know what depth yet, but we're going to go and just click on 4x10, and we'll start with that and see where that puts us. And then the first thing we want to do before we make any other changes, we want to go to our settings here and change this to ASD, and then click on confirm. Okay, so now we have our load duration factor. Right, this just has to do with the type of loading or load combinations you're going to be using in your analysis. So for us, we have dead and live. So we have basically this occupancy live load that we're using. So we'll go ahead and set our load duration CD to 1.0. So let's change this to 1.0. Our moisture content, we are going to assume is going to be less than 19%. We don't have any significant temperature conditions. It is not an incised member, and it is going to not be repetitive because it's just a single header. So we're going to leave that as is. Okay, now that we've got that all set, we can go ahead and click on our beam loading. And we need to enter in our beam length, which is 7.5 feet. Our shear analysis location, because it's a simply supported beam, we know that's going to be at the end, so we'll just click 0. And then the moment analysis, because it's simply supported, we know it's going to be in the middle, so we'll just hit 3.75, and same with our deflection is 3.75. And we'll go ahead and just change this to D plus L because we know that's going to be what our controlling load combination is. We need to go ahead and add in our dead load. So we said we had a dead load of 450 pounds per linear foot, so 0.45 kip per foot. And then a live load is going to be a distributed load of 330, so 0.330. All right, so now we've got our loading set. We've got our shear, our flexure, and our deflection graphs. And we can go ahead and click over to our deflection. Right, and the only thing that's different about timber design for deflection is that we have a long-term deflection that we need to consider, so a creep deflection factor for dead loading. So we have this value here, KCR. There's different options for what type of member you have. For us, since we have seasoned lumber, we're going to change this KCR value to 1.5. And this basically just applies a factor to our dead load. So we take our dead load, we multiply it by this 1.5. And that gives us that long-term deflection for the dead loading, which gets added into our regular dead plus live service load deflection calculation. So just wanted to note that here, that you do need to update this depending on the type of your loading in your lumber. So keep an eye out for that. So let's go ahead and click over to our Flexure Design. Right, we do need to calculate our effective length, right, which is not the unbraced length. So there is a table here, 3.3.3 in the code, and based on your loading and everything, you can figure out what this is. We have a uniformly distributed load, right, and our LU over D is greater than 7, at least to start here with the 10-inch beam. So we can go ahead and use this equation over here. So we have 3 times our depth, which is 9.25. And then we have our 1 plus our 1.63 times the unbraced length, which is 7.5. And that gives us 174 inches, or 175 inches. So we can go ahead and enter in 175 for this. Okay. And then we can start clicking through and see where we are. So we have our bending stress, which is just going to be our moment over our section modulus, S sub x, which is about 1330 psi. And then we have all of our different adjustment factors, right? So we have our load duration, which we already entered, our wet service factor, which is based on the whether or not we're less than or greater than the 19% moisture content. And then we have our temperature factor, which is 1. And then we have our size factor, which, because this is a 4x10, we do have a size factor of 1.2, and that will update based on the size of the member. Flat use, this is in strong axis bending, so that's just 1. And then the rest of our factors are 1 as well for incising and repetitive member factor. Then we calculate our beam stability factor. So first we need to calculate our E prime min. Then we calculate our slenderness ratios, our critical buckling design value, and then we have this FB star, which is the entire equation except for CL, which is what we're calculating, that beam stability factor. So we get our F star, our FB star. And then we calculate our C sub L, which comes out to 0.99, so we don't really have much of a reduction. And then we calculate our F prime or FB prime here for our adjusted bending strength of 1066 psi, right? So we have a DCR right now of 1.25, which is not going to work for us. So let's check our shear, and then we can go back and update our member size. So if we go to shear, right, we don't have any other additional inputs needed for this. It's got everything it needs, and we're at a DC ratio of 0.76. So we're fine on shear. So let's go back to the general tab. Right, and we can see here in our summary, we do have a 1.25 DC ratio for bending and a 0.76 for shear. So let's just go to the next size beam and see if that solves the problem. Great, so we're at a 4x12 now, and that solves our 0.92, so we're below 1.0 for our bending, and we're below 1.0 for our shear. So we are good to go for this header design with a Douglas fir larch number 2 4x12. So that is a timber beam design for sawn lumber. We hope you enjoyed the video, and we'll see you next time.